Hello world, it's Rational Plan. We're back here today talking about the traveling salesman problem and the ridiculous way it needs to be coded. Now, I already tried to put together a code for this problem and, well, let's just say I was not successful. That's the reason I haven't produced a coding video in the last 2 weeks, because I've spent a lot of time doing finals for one, and two, I've been trying to get this code to work. However, I was unsuccessful. I can admit when I can't do something. So what we're going to do is we're going to put together a pseudocode, and then we're going to go out there and we're going to pull some open source information and see if we can get at least some idea of the complexity of this problem. However, I did put together a quick flowchart, and we're going to put together a pseudocode in this video. Hopefully it will work out for us. And I'm probably missing something really basic when I was trying to code it originally. However, when you get a brain block in your coding, it's the most frustrating damn thing in this world. So, let's take a look at the flowchart. So the flowchart itself is very similar to the NBA conferences program we did, all the way up until we create this data table. After that, it's actually pretty simple, but here's the problem with the coding. So, as you can see, we're going to start at each node, and the way the traveling salesman problem works is that you need to find the shortest path, but going to every single node. So it kind of creates a tree, and we'll look at that in a second. So what we'll need to do is we'll need to have a loop that goes to every single node. It starts at every single node. It's going to end at every single node. So then we're going to have a nested loop, and you want that loop to go around n minus 1 times, where n is the number of nodes, minus 1, because you don't want to go back to the original node. You'll also be doing this the whole time, and that's obviously going to be the shortest path, and it's never really going to get anywhere. So we need to then go to the next loop, which is the number of nodes minus 2. And you'll see where the problem is here. You're going to keep going down until you hit the number of nodes. And if you don't know how many nodes you're going to have, it's tough to code this problem. Now, if you know how many nodes you're going to have, you can obviously sit there and code that many nested loops. But if you don't know, or you have a general idea, but you're not 100% sure, this makes it incredibly difficult. And there's ways around that. You could have dynamically expanding arrays that you could use, predictive if statements, but it becomes a pain in the ass, let me tell you. So instead of doing that, I just want to kind of give you a general idea on why this is not a polynomial time problem. And I'll show you with this loop right here is what solidifies this as a non-polynomial time. Because remember, using the big O notation, the computational speed, or the complexity, is based off the number of calculations made. This, I'm going to show you in a second, is the number of nodes factorial. And let's see why. So let's go over here. So we have this tree here. So let's say we start at node 1, and then we go to node 2, and then we go to node 3, and then obviously we're going to end node 4. This is assuming we only have 4 nodes. Then it goes 1, 2, 3, or I'm sorry, 1, 2, 4, 3. So once you get to these bottom 2, you know what the last node's going to be, so that's the only choice that has to be made. That way you can go back in the flowchart here, and then you just say the source path when you get to the final 2 nodes. Because you don't need to then go to the next node, because you obviously know that's the last node. And there's predictive ways of doing that as well. So then you go to 1, 2, 4, 3, then you go to 1, 3, 2, 4, so on and so forth. At the end of node 1, at the end of the overall loop in node 1, you're going to end up with 6 solutions. Well, you got to do that for all 4 nodes. So 6 times 4 is, wait for it, 24! So, okay, 24 is also 4 factorial. 4 times 3 times 2, 4 times 3 is 12, 12 times 2, I believe, is 24, and 24 times 1 is 24. So that, we have now shown, is n factorial. And that's the number of times that we got to make this loop happen, is n factorial times. And that's how many computations is going to go into this program. Now, obviously, there's other calculations where you got to save the information, but those are so negligible compared to the highest level complexity that the overall complexity is just going to be labeled as n factorial. And that's the key here, is that you can have all these one-line statements, but they are so negligible compared to the primary action of the code that you just go by that primary action when you're calculating complexity. So this, the TSP problem, is going to end up being a node factorial problem. So let's just go through how we're going to end up writing something like that. So let's say we have 4 nodes, okay? So we're going to have the namespace, you have the using statements there at the top, class program, yeah, and you can set the global variables, public string main, okay, great. So let's just say we use our NBA conferences code up to this point. Let's make it easy on ourselves. And then, okay, so here's where we need to start calculating the short path. So you want to create an integer shortest path. You'll probably want to create an integer, or I guess it'd be double, because we were using doubles last time. So in double last path, because you're going to compare the last path that you calculated to the shortest path, or to the path that you're currently analyzing. Double. If I could spell, that'd be great. Thanks. And then double current path. Okay, great. So this is going to be the 3 things we're going to keep pushing against each other. You're going to want to initialize them to 0 if you use a code that needs initialization. But anyway, so for int I is equal to 0, I is less than n, which is again the number of nodes, I plus plus, that's how you set up a for loop in C#. Brackets, always, don't ever forget brackets. In fact, it'd always be good practice just go and put the second bracket there too. And then you're going to want to say for int j is equal to 0, j is less than n minus 1, j plus plus, again with the brackets. And then you're going to go again for int k is equal to 0, k is less than n minus 2, k plus plus. And then you only need to go 3 deep because you're only needing to choose 3 different times. Because at that point you're only going to be choosing between 2 different nodes, and then you can compare the 2. So at this point you take the first node, so then you say current path is equal to current path plus, or you could say, in our NBA example, so it was NBA path I dot path plus NBA path j dot path plus NBA path k dot path plus NBA path whatever it is at this point dot path. So that's going to give you your current path, and then you compare it to the next one, and then you go back, do it again, go back, do it again, then go back further, do it all again, and that's where that O to the n factorial complexity comes from. So then you just add all the path costs, and that's what's going to give you your current path. Then at the very end you could say if current path is less than shortest path, then shortest path is equal to current path. Then you reinitialize current path is equal to 0, or I'm sorry, you want to re-establish last path is equal to current path, and and then current path, there we go, is equal to 0, because you're going to go ahead and re-establish all of those things. So that's how you're going to end up setting up all those things, and then at the end of every single for loop, you need to again check the current path is less than the shortest path. And then you're going to want to do that over and over and over again, all the way until the very end. Then you spit out the shortest path to the user. So that would be, let's see, we went 3 in. So then if you're using C#, console.writeLine shortest path. And then you could add some more code in there if you wanted to, explaining the situation. So this is what a typical TSP problem code would look like. This is very simplistic. This is basically just a very simple way of looking at the TSP problem, because if you take a look at larger numbers, so let's pull out our trusty phone here and see how many total paths that we'd be looking at if we had, say, 30 nodes. So that would be 30 factorial, if I could use my phone correctly, that'd be nice. So 30 factorial would be a lot. Hopefully you can see that, but that's 2.65 times 10 to the 32. And that's a lot. So as you can tell, the more nodes that you have, the more crazy this is going to be. So even going from 4 to 5 factorial is 120. So you go from 24 to 120. Going from 5 factorial to 6 factorial, you go from 120 to 720. That's 600 more computations that you have to do. So as you can tell, this is something that is very tough to calculate in a fast manner. I forgot pinkie pie, excuse me. So things that you can do to help with this problem, but however, that sacrifice the idea of solving this specific issue in polynomial time. Well, if you're looking for efficiency and you're just looking for an answer, you could bottleneck certain nodes. So let's say node 1 can only go to nodes 2 and 3. You could bottleneck that. Or you could have a heuristic saying, if the node next to it, if the node that you're analyzing next, if the total path cost is less than the last path, then just forget the rest of that tree. You just go on to the next overarching node. And those are a couple ways that you can go if you just want a quick, rough answer, but that does not solve the PnP problem. The PnP problem needs that you need to analyze and solve the total problem in polynomial time. And right now, I'm not thinking of a way to do that. But there's a lot of people there's a lot of more smart people than me that are looking at this every single day, trying to find a way to solve problems just like this in polynomial time. So that's kind of what the TSP problem is going to look like, but on a very basic and very small scale. Again, that was only 4 nodes, and that would take 24 calculations. Again, if we move up to 5, that's going to go up to 120 calculations, and you can expect as it grows, the time needed to run this program would be immense. So if you get to 30 nodes, the 2.62 times 10 to the 32nd, that's going to take a long damn time. So I'm going to look for some open source code to maybe show you in the next video. If I don't find any that are good or easy to explain, then I'm going to show another PvsNP problem that people are looking at. There's 2 more I want to show. One is Minesweeper, actually, coincidentally enough with my meme sweeper video. The other is prime factorization, where you take a number and then you want to find if that number has only primes as factors. So let's say 3, it only has 2 factors of 1 and 3, that's a prime factorization. So then let's say 21, 7 and 3, they're both primes, that has prime factorization. The problem there is that, yes, it's easy to find the factors of a number, but then you have to compare those numbers and see if they themselves are primes. So then, for every single number that you're checking, it's 2 to the n. Because if you have 2 numbers that are factorization, or if you have 2 numbers that factor into a number, that's 2, and then you have to check those numbers each time to see if they themselves are prime. So it's 2 to the n complexity, and we'll show that in our next video. Hope you guys are enjoying this so far. I understand this is pretty complicated, if it's complicated yet simple at the same time, so there's a lot of questions you may have. Please comment below. I'm always available on Twitter, Facebook, whatever, and I will see you guys in the next video. Have a great day.